This module and the next couple will be looking at data structures called graphs, which can be used to solve lots of interesting problems. So we'll both look at graphs as a data structure themselves and algorithms that operate on graphs. So just kind of a quick review of data structures so far. We've largely been focused on access patterns. So we've looked at access based on using an index with just the generic concept of an array. Then we kind of abstracted that to the idea of a list, and we looked at different implementations of a list. So implementing a list with links versus implementing a list using an actual array. Then we looked at access based on arrival time with the queue and the stack. So queue is first in, first out. Stack is last in, first out. And then we looked at the idea of access based on importance or priority with the priority queues. And then we started looking at access by using some sort of a key to look up or find data when we started looking into maps and dictionaries. Okay. So in addition to all of those different access patterns, we've also looked at a couple of different types of collections of data. So unique data can be stored in a type of collection called a set. And we also kind of looked at the idea of ordered data, and that this isn't separate from being a set. We can have ordered sets. So when we were looking at ordered collections, we were talking about binary search trees and the AVL tree and the 2-4 trees. But you can also have ordered sets or ordered collections by using lists, or lists based on arrays or lists based on links. Okay, so a lot of our prior data structures were organizing individual pieces of data. It was kind of a collection of things that are all the same. Graphs have a little bit more complicated capabilities. So graphs are used to organize relationships between pairs of items. So this kind of overlaps the discrete math concept of a binary relation. So the idea of a relationship and a binary relation from discrete math are largely the same. And the name graphs kind of implies that this might be shown graphically. So it is a little bit different than the notion of computer graphics, which is about drawing pictures on the screen. But there is kind of a graphical depiction of things. So I'm going to work through a couple of examples, and we'll use these to kind of understand notations and terminology that we're going to use as we work with graphs. And then in other components of this module, we'll look at actual implementations and some algorithms that can be used. Okay, so here's a kind of a simple sort of relation we might want to deal with. We might want to represent the concept of one person working with another in a workplace. So this is kind of a type of social network, indicating the connections between different people in this case. So here I have a kind of a graphical depiction of several different people, Chris, Brad, Bill, Michelle, Kate, and Anne. So this is based on one of my prior workplaces. Okay, so there are different relationships in this workplace. So some of us work together directly, and some of us do not directly interact with others. So for example, I worked with Anne, and I worked with Chris, and I also worked with Kate and Brad. But I didn't work directly with Michelle. Kate worked directly with Michelle. Okay, so here we've kind of formed a graphical depiction of who works with who. And we've done that by using these circles to indicate individual people, and the lines connecting those people to indicate the existing works with relation. Okay, now there might be a little bit more to this graph. There might be a couple of other people like Amber and John, and maybe they work together and are kind of separate from the group of us. So an entire workplace might have these kind of 8 different people, some of which are somehow connected to one another, and others which are completely separate. Okay, so let's introduce some terms to be a little bit more formal about this. So the things that are related are referred to as a vertex or a node. So in my example, each of the people would be considered a vertex or a node. The indications of things that are related somehow, in this case related in the sense of working with one person or working together, are referred to edges or arcs. So all of those lines that connected things together were the edges or the arcs of this graph. Of course, those edges and arcs don't make any sense separately like this. They only make sense in the context of the things that they connect together. Okay, so why might we be interested in this sort of a graph? Well, there's some different examples. So you've probably already experienced this in real life if you use either LinkedIn or Facebook, where it recommends people you may know. So it does that basically by representing people in some sort of a graph data structure and then using some algorithms to figure out close connections. It can also be used to identify potential strengths and weaknesses. So in a social network like this, it can be used to identify isolated groups or individuals. So in our previous example, we had kind of a cluster of 2 people who worked together, and they were kind of separate from the rest of the group, Amber and John. Okay, so more formally, we can represent graphs with a mathematical notation. We can represent a graph G as being a set of 2 different things, or a collection of 2 different things. One of those things is V, the vertices. It's a set of vertices or nodes, and the other is E, the edges. So by the way, notice that I said set of vertices. So we think of this in terms of the concept of a set, in that each vertex is distinct. We don't have graphs with 2 vertices that we'd consider to be exactly the same. So for example, in my social network graph, if there were 2 people with the same name, we would probably somehow indicate they were different. Maybe if they have the same first name, we will also include last names to indicate they're distinct. Okay, so when I said set of, really what I'm talking about is that each vertex is distinct. Now, what I don't mean is that we're specifically using a data structure that's called a set to represent these. We might, but we don't have to. In fact, oftentimes these are represented with some sort of a list data structure. So, again, set of vertices means distinct. It doesn't necessarily truly mean a set data structure. Edges are typically represented as a collection. So I say collection rather than set because there isn't necessarily this idea of things truly being distinct. More on that a little bit later, and we'll talk about some of the details we might have to worry about when we talk about implementing these. So an edge is really just a connection between a pair of vertices. So the edges are primarily defined by the vertices that they connect. There may be some additional accessory data, as we'll see. Okay, there are lots of terms that go along with graphs and lots of different variations. So I want to kind of go through an example and all of the different terms and kind of distinguish what the terms mean with respect to this example. So list of terms, one of the things we'll encounter is a graph that's referred to as a simple graph versus a graph that's not simple. We'll also see directed versus undirected graphs, multigraphs, acyclic graphs, or a graph that isn't acyclic, that has cycles, weighted graphs, or graphs that don't have weights, and we can have kind of combinations of these. So almost every graph we'll talk about will have some set of these or have some of these properties that are absent. So one of the things that we'll see soon is something called a directed acyclic graph, or a DAG. So as the name kind of implies, it's a kind of a combination of both being directed and being acyclic. So it's a combination of 2 of these properties. Okay, I want to go ahead and take a look at another example. So I want to look at kind of a common example of a flight distance relation. So here, when I say distance, what I really mean is time. So we could kind of think of how far away some place is, its distance in terms of the amount of time it takes to travel there. And in this case, I'm going to think of flight time, so flying from one place to another. And I'm going to maybe assume that this is a specific 4-hour window starting at some time. So I'm not necessarily keeping track of all possible flights over all time. I'm not looking at all possible cities. I'm just looking at a specific set of cities and some small set of flights, again, perhaps in a 4-hour window of time. So I'm looking at several different cities here: St. Louis, Chicago, Detroit, Atlanta, Houghton, and Isle Royale, which is an island in Lake Superior. Okay, so the connections here kind of indicate if there happens to be a flight from one place to another. Okay, so I want to introduce a new concept now, this idea of distance we're going to represent with something called weights. So a weight is a numeric value on an edge. So if the flight from St. Louis to Chicago takes 74 minutes, I would label that on the edge between St. Louis and Chicago. And I could do that for the flight from Chicago to Detroit that might take 84 minutes, and so on. I could apply weights to all of these different edges. Okay. Now the reason I might want to do that is because it might help me solve a particular problem. Maybe I'm trying to figure out the fastest way to go from St. Louis to another city. And by fastest, for this example, I specifically mean the total amount of time spent in the air is the minimum. Okay, we'll come back to some of the different types of problems we could solve later. Okay, so you may have already thought about this and realized that this picture doesn't quite capture everything that's important here. So I've drawn these arcs with just simple lines connecting things. And that worked for our social network example. So if I work with Chris, Chris works with me. It's a symmetric relationship. So that's not true for flight distance stuff. If we're thinking about these in terms of flights, the plane leaves a specific airport and arrives at a specific airport after some travel time. So we could represent that concept with arrows. So in this case, the arrows clearly show where it arrives to. So in this case, the arrow points towards the destination. So we can leave St. Louis and fly to Chicago in 74 minutes, or we can leave St. Louis and fly to Atlanta in 85 minutes, and so on. Okay, so the directions are an edge with a specific direction. So this represents a directed graph. Okay, if the edges have directions, it's considered a directed graph. As we saw with the social network graph, sometimes the relationship just doesn't really have the concept of a direction. Here, there's clearly a concept of a direction, a start and a stop. Okay, so far we've got a graph with two properties. It is a directed graph. It is also a weighted graph. So in terms of our list of terms, we've kind of knocked off two of them. So let's go ahead and look at a couple of others here. So back to our example. So one of my friends happens to be a private pilot, and he always takes his airplane out from his home airport, which in this case could be considered to be St. Louis. He takes it for a spin, enjoys his day flying, and then lands back at the same airport he started at. So we could depict that with an arrow going from the one city back to itself. So this is sometimes referred to as a self arc. Of course, we could apply some time to this. I don't know, maybe it's 30 minutes of flight time. It's probably a lot longer than that. Okay, so this particular graph would not be considered simple. A simple graph lacks these self arcs. So if I remove that self arc again, it's now a simple graph. There are no self arcs from a node back to itself. Okay, so that takes out our next term, simple graphs. So we've still got a couple of terms left to look into, multigraphs, acyclic graphs, and we'll come back to the combination graphs at a later time. Okay, so let's continue to expand this example. So this is a slightly updated example. So one of the things I want you to notice about this example is that I can leave St. Louis, I can fly to Atlanta, and assuming that the flight times align, there might be a flight from Atlanta to Chicago, and then maybe if the times line up again, I could take the Chicago flight back to St. Louis. So this represents a circle or a loop, or what's called a cycle in a graph. Okay, so this has at least one cycle, so it's a cyclic graph. So one class of graphs is acyclic graphs. So here I'm back to my original graph, which had this arrow going the opposite direction of the version we just looked at. So this particular graph would be considered acyclic. If we look at it carefully, there are no cycles. There's no way to start at a particular node like St. Louis and follow the direction of the edges and get back to that same node. Okay, so acyclic. Okay, so we've got one more term to cover, the concept of multigraphs. So a multigraph just has edges that in a sense are redundant. They may start, we may have two edges between the same set of vertices that go the exact same direction. So in this case, this kind of indicates that there are two flights from Chicago to Detroit, maybe on different airlines. One takes 84 minutes and the other takes 87 minutes. So the edges may not be completely identical in every way. They may have different weights, but they connect together the same set of vertices in the same direction. So this would be considered a multigraph. Now, if one of these were going the opposite direction, they would be considered, it would no longer necessarily be considered a multigraph. So again, the important part here is that we connect the same vertices in the same direction. Okay, so edges that are redundant. Okay, so back to our previous example. So again, this is not a multigraph. This is the version that does have a cycle, though. Okay, so with that, we finished up most of our terms. Based on those terms, we now know what both a directed graph is and what a acyclic graph is. So a DAG is just a combination of both of those properties, being directed and being acyclic. Some additional terms here. We refer to an edge as being incident to or entering a particular vertex. So in my previous example, this edge that was, I think was labeled 74 would be considered incident to St. Louis. It would be considered incident from Chicago. A node is adjacent to another node if there's an arc to get to it between them. So in a directed graph like this, we would say that St. Louis is adjacent to Chicago. There's a way to get from Chicago to St. Louis, a direct way over a single arc. But we wouldn't say the opposite because there was no reverse going arc to go from St. Louis to Chicago. So in this particular example, Chicago would not be considered adjacent to St. Louis. Okay, a couple more terms. So there's the concept of degrees in nodes. So in an undirected graph, the degree is the number of incident arcs. Okay, basically it's the number of arcs that touch a particular node. In a directed graph, we can actually break this down into two distinct concepts. The concept of in degree, which is a count of the incoming arcs, and out degree, which is a count of the outgoing arcs. So in one of our previous examples here, we'll kind of focus in on Chicago. So Chicago has a total of 4 different arcs touching it. So the out degree would be the number of outgoing arcs, and it looks like there are 3 different flights that leave Chicago. And the in degree would be the number of incoming arcs, so the total of 1 incoming. So notice that those sum up to be the total number of arcs connected to Chicago. Okay, so why might we be interested in this sort of relation? So I've already answered this a little bit earlier. So it can be used to answer several different questions. One of them is just the most basic question: can I get from one point to another? Can I get from here to there, or from there to there from here? Okay. We can also be a little bit more precise about that. So we might be trying to optimize things. So this might use slightly different definitions of vertices and edges, but typically the vertices would still represent some concept of destination, and the edges somehow relate to the travel time. So we could be trying to do the lowest time in air, which will work with the definition of vertices and edges we just used. We might be trying to get someplace with the earliest possible arrival. So maybe I know that I'm going to leave on Wednesday, and I want to arrive at a particular destination as early in the day as possible. So earliest arrival time. In this case, the edges may not represent flight times. They may actually be related to arrival times instead. We maybe want to minimize the overall distance, which would correspond to plane fuel. Maybe we're actually focused on cargo capacity instead. Maybe we've got to ship a lot of packages from one place to another rapidly, so we're using air freight. And we want to use as few flights as possible. Okay, so I want to look at two more things in this component of the module. I want to talk a little bit about generic graph notation. So oftentimes we represent nodes just with single letters when we're talking about graphs in kind of a generic sense. So instead of naming them with cities, as I was doing earlier, we might just refer to them generically as node S, T, U, V, W, and X. Okay, so we oftentimes just use single letters for the nodes and vertices. When we do that, then we can describe arcs as a pair of letters. So for instance, I've got this arc here that connects T to S. So I could just describe this as some sort of a vector or a pair, T and S. So of course, we also have to keep track of the associated information, the 74 minutes that represents our weight. Okay, so my generic graph here could just be thought of in terms of vertices and the 6 different pairs of vertices that make up all of the arcs. And then, of course, for each of those pairs, I would also probably want to keep track of the weights for this weighted graph. Okay, so we've looked at directed versus undirected graphs already. So in general, you probably want to use undirected if all of the relationships are symmetric. So again, like this coworker or works with relationship is always symmetric. A can't work with B unless B is also working with A. Okay. So if we are working with an undirected graph, sometimes we'll still denote edges as though they're a pair of items, but the idea of first and second no longer matters. So if I've got an edge between U and V, the notation of the pair UV indicates that this actually goes both ways if I'm talking about a truly undirected graph. Usually when you start working with graphs, you decide up front whether you need a directed graph or undirected graph. And if you're working with an undirected graph and you see a pair of vertices like this, you assume that that's an edge that goes both directions. So it means that both U connects to V and V connects to U in our undirected graph. Okay, so I wanted to review some examples in a little bit more detail. So we've already looked at this idea of social networks. The vertices in my particular example were people. The edges were some relation like works with or directly knows. They indicate a direct connection between two people. It was an undirected graph. We didn't have any sorts of weights on those edges. It was a simple graph. The concept of directly knows or works with oneself doesn't exactly make a whole lot of sense. It's not typically useful in the types of problems we explore with social network graphs. And it also wasn't a multi-graph. I mean, if A works with B, there's no reason for a secondary edge connecting A and B. Okay, so we also looked at this idea of some sort of a transportation network, flights going from one city to another. So this does have some correspondence to an actual geographical map. The vertices represent the places of interest. You can kind of think of it as your starts and stops or your destinations that you want to go to. The edges represent the actual transportation between them. So it could represent roads, it could represent flights. Okay. It was a directed graph because we saw that as you talk about flights, there is a distinct start and a stop. Oftentimes it's a weighted class where the weights represent the time or the cost in some sense of going from one of the locations to another. And generally it's a simple graph. We're usually not terribly interested in these sorts of transportation graphs with self-arcs, with the exception of those examples where, like at the airport, someone leaves from a particular airport and flies back to that same airport because they're just taking a hobby flight. And oftentimes transportation networks are truly multi-graph. So we already saw the example of that with the airline example where there might be two distinct flights from city A to city B. It's also true in road networks where there might be two different roads that directly connect 2 points. So it's not uncommon to have a road that parallels an interstate, a highway system, and they both essentially connect the same 2 points. It's just the highway maybe goes on and has fewer traffic lights and signals and such. Okay, another example is kind of personal to me. It's electric power systems. So a large part of my graduate work was related to electric power systems, and I was working with a large group of people, and they were trying to decide how best to add additional equipment to the power systems that would minimize cost and also improve the power system's ability to respond to blackouts. So the goal was to try and avoid blackouts, prevent power failure one place from spreading through the network and causing other power failures. So as we were trying to model this system, we were really concerned about the places that create power and the places that use power, so generators and consumers. For our purposes, the generators were things that generate a lot of power, large power plants, wind farms, possibly solar farms. And the consumers tended to be substations. We weren't worried about an individual single person using power at their home. We were really concerned about the substations that distribute power to entire cities. Okay. The edges in our graph were basically the power lines that ran across the country connecting generators to the consumers. Oftentimes the generators are out quite a ways from cities. And of course, the bulk of consumers are in some sort of city setting. There are certainly smaller customers out in rural areas, but oftentimes they go through a large power substation in a more urban area to get their power. Okay, so for our work, we didn't really consider power lines to be directed. One of the things we were trying to utilize was underutilized power lines, and we might be changing the direction of flow in them to control aspects of the power flow throughout the entire power grid. So we wanted to think of power lines as going both directions, so we wanted to implement them as an undirected graph. In our case, it actually was a weighted graph, so we were trying to make sure we utilized power lines but didn't exceed their maximum capacity. So the weights in our graph tended to be the maximum limits of what the power lines could carry. We also were working primarily with simple graphs. We didn't really have any self-connecting edges. That would kind of imply that something was both a generator and a consumer. And although that is true to some degree, it wasn't the aspect of things that we were trying to model. We were trying to model large amounts of power going from large generating areas to large consuming areas. And it was a multi-graph. There were places in our example network, which was based on the east coast of the United States, where there were parallel power lines, multiple power lines that basically went from the same start to the same destination. Okay, there are lots of other examples. You can model financial transactions, A selling to B as a graph. So the individual people or entities involved in the transactions represent the vertices, and the individual financial transactions represent the edges. Web pages and the internet can be represented as graphs, so the page itself represents the vertex, and a hyperlink going to another page represents an edge. Communication networks like telecommunications networks, phone networks, etc. can be represented. There are lots and lots and lots of problems that can be represented as graphs. It's a really useful concept for certain types of problems. So let's talk about some graph considerations that may be handy to us as we start talking about implementing things and come back to the idea of time complexities. So if we've got a graph G that is a collection of vertices V and edges E, for the next couple of minutes, I'm going to assume that we're using lowercase n to represent the number of vertices in V. And I'm also going to assume we've got a very specific type of graph. It's both simple and undirected. So the edges connecting things do not have arrows. If it connects something, the connection goes both ways because it's an undirected graph. It's simple in the sense that there are no self-arcs, and it's not a multigraph. Okay, so one of our questions is, what is the upper limit on edges. And again, this all comes back to this idea of complexity. So we'll be interested in how much space it takes to store graphs, and that varies with the number of edges. And we want to find an upper bound on that. We'll also be concerned about time complexity, which oftentimes depends on the number of edges. So let's sketch an example here. So I'm just going to make up a couple of different nodes, and I'm just going to draw them on the screen here in no particular order, so they're kind of these little circles. And I'm going to think about the number of connections. So in this specific example, my n would be 5. And I'm just going to arbitrarily pick one of these, and I'm going to try and make as many edges as possible within the bounds of what I can do. It can't be a self-arc because it's a simple graph, and it's not a multi-graph, so I can't have the same arc going, redundant arcs going from one vertex to another. And it's undirected. So I'm going to start at the node at the upper left. It can go to its neighbor to the right, and then it can also have an edge down to each of the 3 other nodes in the graph. So of my 5 nodes, the first one that I started connecting together could have a total of 4 arcs outgoing. And I can kind of repeat that process. So I'm going to go ahead and move over to this second vertex, the one on the upper right. And it's already connected to the one on the upper left, so I can't add another connection there, but I can go ahead and draw a connection to each of the other 3 nodes. So that adds another 3 connections. At this point, you probably already kind of see the direction of where this is going. I'm now going to focus on the vertex in the bottom left, so it can be connected to 2 of the remaining nodes. So that adds another 2, and then I'm kind of down to my last vertex here, connected over to the rightmost vertex. That adds another 1. And at this point, the graph is kind of fully connected. I can't add any other arcs and continue and still have a simple undirected graph. And you may notice kind of a familiar relationship here. So this is actually the sum from 1 up to and including n minus 1. Okay, so we can apply the formulas that you've already seen and used often in this class. So n minus 1 times n minus 1 plus 1, which is just n over 2. Okay, so our answer is n times n minus 1 over 2. Okay, so that's the maximum number of edges that are possible in a simple undirected graph. Okay, what if we change the problem just slightly? And let's assume that we now have a directed graph. So that only changes the previous problem just a little bit. So I'm just going to focus on 2 of these nodes. So previously we had, in our previous example, we drew a connection between them. And when we add in support for direction, we now have to think about whether this goes this way or whether it goes the other way. So for each of our arcs in our previous example, we've now just got 2 options. We basically double the number of arcs that we could have in the undirected graph. So total number of edges that are possible is n times n minus 1. Okay. Okay, in either case, the maximum number of edges is basically big O of n squared. So this brings us to 2 more terms. If the number of edges we have is on the order of n, it's considered to be a sparse graph. Okay. It turns out a lot of practical graphs, in fact probably the vast majority of practical graphs, are sparse graphs. So if you think about a social network like all people on Facebook, each person maybe knows a couple of hundred people, but probably not the millions and millions that are actually in the network. There might be a few outliers who know thousands or tens of thousands or possibly even connected to millions, but by and large the vast number of people are connected to several hundred to thousands of people at most. Power transmission systems are also very, very sparsely connected. Oftentimes a substation is connected to, I don't know, maybe 2 to 4 different power sources. So it is on the order of n. Roads are also pretty sparsely connect different destinations. So a lot of practical examples are considered sparse graphs. Graphs with big theta of n squared edges are considered to be dense. So There aren't terribly many examples of this. If you're doing some sort of a physics system where you're trying to simulate the interactions between all pairs of items, so like gravity in a solar system, if you really want to know the total impact of gravity, you have to add up the contribution of absolutely everything in the system. So that would be an example of something that can be represented with a dense graph. Okay, two other notations that are kind of common are the number of vertices is often described as being the size of the set of vertices. So the common mathematical notation here is to use something that looks like the absolute value bars with the set inside of it. So absolute value bar, V is the set, absolute value bar. So I've been referring to this as N earlier, but because we have these two different collections that have two different sizes, it's really common to see this alternative notation rather than using a variable like N. So the size of set V and the size of collection E. Okay, so there's some common special graphs that you may encounter. So the complete graph is a simple undirected graph where every pair of vertices is connected. So when we were coming up with our argument for the maximum number of edges in a simple undirected graph, we basically constructed a complete graph. Another common concept is the bipartite graph. So in a bipartite graph, vertices can be divided into two distinct sets such that all edges go from one set to another. So I'm just going to draw kind of a very small example here with just 5 different things. So if I had something that I don't know, looks like this, I could pretty easily divide this into 2 sets, so that the top set and the bottom set, and all edges go between these 2 sets. So I could actually break this by drawing an edge between 2 different vertices like this. So again, a bipartite graph is kind of about dividing into 2 distinct sets where all edges connect between those 2 sets.